captioning on videos. Basically, we try to solve video perception using deep learning. Okay, say those. Okay, so today we're going to talk about connectionist temporal classification. Feel free to interrupt me at any point in time if you have any questions or if I'm not here. So let's start out with the outline. We start out with the motivation for CTC. Then we talk about aligning outputs and labels. Then we talk about CTC loss, default backward algorithm. How do we backdrop after calculating the loss? And then we finish up with some conclusions. Okay, so the motivation is a popular loss function such as cross entropy and mean square error. Assume that there is a one-to-one correspondence between the outputs and the labels. So if you have 10 target labels, you assume that there are 10 outputs in order to compute the cross entropy error and the mean square error between them. But what if there is no one-to-one correspondence? So for example, in speech recognition, the input is a bunch of phonemes, and the output is a character, the input is usually a sequence of waveforms or a spectrogram, and the output is a character or a phoneme, and so multiple time steps can correspond to a single phoneme. Same thing with online handwriting recognition. You have X and Y coordinates of where the pen is and whether it's touching the paper or not, and you need to figure out which character was written. And so every character requires more than one X, Y character. And so we need to find out how to align the network outputs with the labels. Okay? So this is where CTC comes into play. So given a sequence of n inputs and m labels, we want to compute the loss between the n outputs and the m labels. So we're assuming that since we have n inputs, we also have n outputs. And the number of outputs don't necessarily equal the number of labels. So we have a waveform example here. And you can see that, for example, the takes some particular number of time steps, takes even longer, S even longer, and so we have, for S, we need more inputs in order to capture the S. For D, we need less. And so we can see that we need to figure out how to align this, for example, phoneme with this envelope, or at least approximate that somehow reasonably. And so how do we do that alignment? Basically, we define a function that allows us to collapse repeated letters together. Just bear with me. We also define a new token called blank, which will be represented as a dash. So for example, if we have an input of length 8, we can define a function such that if I get hello, HELL-LOO, we could first collapse the repeated letters to get HEL, blank hello, and then we remove the blank symbol, and then we get hello. At the same time, if we get HE 4 L's and then 2 O's, the repeated characters collapse. And so we end up with a single L and a single O. Clearly not what we want. The same thing goes for this example. Here we collapse the blanks and then we remove them. Finally, you see the pattern in there. And so let's establish this convention where I have the time steps on the horizontal axis and the labels on the vertical axis. So let's say that I want to draw the path for HE, E-L-L. So we start out with an H, we go to E, then we go to E, then there's dash, L-L-O. So this basically tells us we have 8 time steps. If we collapse the whole thing, if we apply the function that we have previously defined, we get the normal hello. Same thing here. Okay, we can see how we traverse through the nodes in order to actually, in order to get that input. And we see how, if we apply the function on the input, we get this output. And so if we look at this, we have 5 labels and we have 8 time steps. So there are 5 to the power of 8 paths in this entire grid that allow us to go from T1 to T8. And so that's over 390,000 possible paths. that means if we want to maximize the probability of HELLO given all possible paths, we will have to compute all possible paths and then maximize whatever paths correspond to HELLO. And as we have seen, that can be multiple paths. And so clearly we cannot compute that probability after computing 390,000 possible paths. That's intractable. And so what we want to do is to figure out a more efficient way of doing this. And this is the whole concept behind CPC.
Can you, how does it generally scale? Because how do you know that that's 5, not something else?
Sorry? It can be anything. This is just an example. So yeah, if it's 10, it's even worse, as you can see. If the number of time steps is larger, it's even worse. So in speech recognition, this actually can be very large.
Sure, that's what I'm asking about. Is that like an exponential scaling?
Well, this just motivates the approach that CTC is going to resolve. So CTC is going to solve this problem.
Right, but the problem that you're talking about, is that an exponential scaling?
Yes.
Or okay.
Yes, it's basically the number of paths are increasing in an exponential manner. And so if we want to compute the alignment over whatever we're interested in, it would be very, very expensive.
The length of the unit is fixed?
Sorry?
The length of the unit is fixed?
Well, usually, you mean as in the number of time steps? Yes, it would be fixed. I mean, when you, in practice, in theory, there is nothing stopping it from being fixed, but in practice, you deal with tensors. Those are usually fixed length.
Yeah, because in the discussion about the waveform, so I wonder if the length of the waveform.
Oh, you discretize it. The waveform gets discretized every 20 milliseconds. That's sort of a single.
You're not fixed.
Yeah. Usually, also compute the Fourier transform or some sort of spectrogram.
You discretize it in like fixed time steps.
Yes, 20 milliseconds.
Okay.
You take 20 milliseconds.
If I take a really long time to say the word hello, that's more time
Well,
steps.
yeah, we're actually going to cover that. So
So I have a question. So I mean, it's exponentially many paths through that thing, but like there's like hidden Markov models for that for this same problem as well, and they kind of deal with like if you have a Markov assumption for the natural language or trigrams are pretty much very accurately modeled with those. You don't have to be necessarily exponential.
yeah, that's true, and it is going to use actually Markov models to overcome this. Okay, so far so good. Okay, so let's go next. Can't go next. Does it work? Oh, no. Okay. So in CTC loss, we would like to minimize the log probability of the word. And so let's say for the word hello, we would like to minimize the negative log probability of hello. One thing to keep in mind is that we need this hello after applying our function. Okay, it's not something that we want to get immediately, it's something that we get after applying our function. And so as we saw, this cannot be solved trivially, otherwise the number of paths explode. And so the solution is basically dynamic programming. So how is this done in practice? Well, as we saw previously, the time steps are on the horizontal axis. On the vertical axis, we actually have the ground truth labels, which are the ground truth characters, and we have a blank symbol separating them, as well as a blank symbol in the beginning and a blank symbol in the end. So hello is like 5 characters, so the whole thing is 11 characters. So let's say that I would like to plot the trajectory of the blank HEL blank L O blank. So I start off at blank, go to H, from H go to E, then there is an L. Note that I can skip blank symbols, but I cannot skip characters, otherwise I'm not getting one of the valid paths. So between L and L, I have to go through a blank, otherwise it would get collapsed, and I would have only a singular. Then I can go to home and then blank. So basically, this is how the whole thing looks like from the first time step to the 8th time step. Okay, so far so good. Note that in this convention, we are only allowed to go across and down. Okay, we're actually not allowed to go up. And that sort of simplifies the whole computation, but it also means there is an inherent assumption. We need to know the order of the labels. So we need to know that H happened first, then E, then L, then L, then O. Okay, otherwise this breaks and the whole thing becomes much more complicated. Okay.
So this is for training, not for inference.
Yeah, this is for training.
Okay.
Yeah, I'll be mainly talking about training in this talk. Inference can be done multiple ways, but there are like CDC decoders, or even a trivial argmax decoder can sometimes take you. Anyway, so and we have. And so we can plot alternative paths. For example, second path, we start out with a dash. We start out with a dash to an H, then we go to E, L, dash L. Then, for example, we have another L. That's why we have double L, and then O. And so all of these are valid paths. They're valid paths through the grid that would give us hello. And so we can see if we plot all the possible paths, we kind of get this grid, which is way less than 5 to the power of 8. In this case, 11 to the power of 8. And we can see that it actually captures variations in pronunciation. So we can have something that's someone who has a pause in the beginning, then says hello, to saying hello without a pause and pausing in the end. We can also have this utterance hello. And so as you can see, if we have a large number of time steps, we actually have more flexibility. So any questions? Yeah.
This is for particular Y, which is hollow Y. So I wonder, like, is the neural network the Y, all the possible character would be the alphabetical character, right? So how does that work? In this particular case, you're just predicting hollow, and that's how you can walk down the path. But I believe there's much more character in the predicted Y value in there, right? Because you are processing a bunch of random observations, which probably may not be one of them. Just wonder how does those characters being played with this example in there?
Well, if you're asking about how to backdrop to the network?
No, I mean like it's right now every time step in there, like the vertical one is basically the possible Y value in there, right? Which is like the number.
Yeah, the possible ground truth value. So I take the value of the network here, I try to maximize H and I try to maximize Y blank. I try to maximize the probability of blank on the first time step. In the second time step, I try to maximize the probability of these.
Right, but this is for a particular example, which is hollow, right? But
yes.
what if the other input is like not hollow, but like good morning or whatever, and one of those characters in this
The vertical line.
Yeah, the vertical
Yes,
line.
it's going to be pretty much the same thing.
Yes, you know the ground truth.
Yeah.
Yeah, you know the ground truth. You have to give the ground truth.
This is a training setup.
Right, but I mean like, because you're training, you don't just train on one example, right? You have more.
No,
We
but
have
this-
to do it for each example.
Oh, I see.
Yeah. Each canonical example. So yeah.
Yeah, and one thing also, this is something to introduce the method because it's quite tough to understand from the paper itself, and so that's why I'm trying to give an example, like a real example, because it makes the whole thing much more digestible, at least in my opinion. Okay. So, in order to compute the CTC loss, we have a forward variable alpha, which calculates the total probability from the first time step T1 until time step T and token S. And then we have a backward variable beta that calculates the total probability from the time step T token S till the end, which in our example is T8. And
Sorry, hold on.
Yeah.
Can you go back? I didn't think what you said.
So we have two variables. We're having a forward variable and a backward variable. So the forward variable goes from calculates the probability, the cumulative probability of token S at time step t with respect to the first time step, and this one calculates the probability at time step t of token S with respect to the last time step. It makes the whole thing much easier, as we will see.
So can you put it in the example framework, the hello example? What's small frontier, like just?
Yeah, we'll go through that.
Okay.
Next slide.
Patience. Yeah, next slide. Yeah. So let's say we want to calculate alpha 3 or 4, so we go to T3 and the fourth token, which corresponds to E. And so we can see that there are actually 4 paths that get us here from the beginning. And so here in the beginning, we can either start from blank or H. And we try to see how many paths can get us through alpha 3 or 4. We can see that it's blank HE, H H blank E, and HEE. And so note that these are the network outputs. These are the softmax probabilities of the network. And so we take the probability of blank at time step 1 that is output by the network. Okay? And so to get the probability of blank HE, we have to multiply the output of blank at time step 1, H at time step 2, and E at time step 3. And so you can generalize it to the rest of the examples. You can see that the final probability of alpha 3 or 4 is just this sum. Because we're trying to figure out how many paths get us to that particular token at that particular time. Is that clear? Sure. And so you can notice how dependent this node is on the last 3 nodes. And so one way to simplify this calculation is to calculate the alpha for token E at time step 2, token blank for time step 2, and token H at time step 2. And so if we sum them up, all what we have to do is just multiply the sum with the probability that the model outputs for E at time step 3. And this way we can get the forward variable. And so we do that for the entire frame. The general equation is here. This is just one case. There is another case where we have a blank. So we cannot go from blank to blank. Otherwise, we skip a ground truth character. That's not allowed. And so we will only take the last 2 forward variables into consideration and multiply it by the network's output for blank at time step 3. Similarly, if we have two similar characters, we cannot go from the character to itself, otherwise it gets merged. And so we only take the last 2 time steps in order to avoid this merging issue. And so we can see that in general, the equation for these types of cases just ignores the one that's 3 tokens. That's 2 tokens of alpha. Note that if we calculate the alpha here towards the end, if we sum the alphas of these 2 nodes, we actually get the full probability of hello. We have essentially calculated the likelihood of the network outputting hello in the way that we have defined this function that merges and removes blank symbols. So this is basically the end of the explanation for the forward calculation. Do you have any questions?
What is Y again?
Y is the network's output. So basically, you look at the network's output at the 3rd time step. Okay, you look at that vector, and you see what's the probability of blank there. You take it, and you plug it in.
And when you say networks output, what network are you talking
The model. The model's output. I think of it as a deep learning model. Yeah.
So I guess my question to the earlier question in this case is that because in here you're just considering 5 character, right? You're basically ignoring all the other probability, right? There's C and
Yeah, because they don't exist. No,
Okay,
because you want to identify hello. Okay, so you actually don't care about C.
so you just
or-
pick the one that you care and do this thing.
Yes.
I see.
Yes.
Can you go back to the previous one? How come there's 3 terms there? And
Okay, so here we have a character that's not repeated, and it's not a blank. It's not a blank, and the character before it is not itself.
okay.
Yeah.
I think it's not necessary to stop at T8. Your word can stop at T6, right? So because H, E, L, blank, L, O, so you stop. So just know that alpha 8 here, so alpha 6.
Well, you're saying that I should stop here?
Yeah, and then you can.
Well, it largely depends on the application that we have, right? Usually we're dealing with fixed size tensors. So in some cases, yes, I'm gonna, if for my application I saw that 6 is the largest number of time steps, then yeah, I'll stop here. But we're just assuming that in this case, we stop at the 8th time step. I could have said we should stop at 6, I could have said we should stop at 12. It's just that there are too many paths if it's 12. And if it's 6, it's not satisfying.
I mean, yeah, and there's a maximum time step for work. Some people speak fast and do slow.
Yes, and having these different paths captures that. So let's say that we go to the topmost path, right? We have blank, then H, E, L, L, O. So that corresponds to someone delaying a little bit and saying hello. There is also another case where, for example, if we have H, E, L, 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 so someone says hello and then hello. Okay, so these paths do take into consideration different ways of pronouncing hello, given that the number of time steps is 8. If we have a larger number of time steps, then yes, we do capture even more different ways of pronouncing hello, and that's what happens in practice. In practice, there is like more than, I think, 10 time steps for one character or something. Okay, and so it's totally up to you. You have to trade off computation with your application, and so in the real world, this is actually not a problem.
So it's basically an empirical number. So you choose by experiment. You think that's the best number?
The speech recognition TIMIT has sort of one of the standards is 20 milliseconds, and so if you think that each T is 20 milliseconds, if it takes you, for example, 1 second to say hello, or even half a second to say hello, I think that's already like 25 times the. 1 second is like 25, 14, 50 times. Yeah, 50 times.
But some words very long. So how do you choose the longest time step? So basically you use the.
Okay, so usually you would have usually you would have the speech segmented somehow, and you would have the ground truth label to it. And basically that's it. It's a weak labeling problem kind of thing. So you have your input, and then you have your output sort of ordered, like H is in the beginning, E, L, L, O, so on and so forth. Yeah.
What's the impact of the time interval? Basically, here you have 8 times, let's say you have 20 or 4. What's the impact of this partition in the final optimization problem?
Okay, so
the more times that we have, the better result, or which one is it?
well, you would so if you have more time steps, it allows you to be more fine-grained in your alignment. But at the same time, it requires more computation. You have to do, all of a sudden you have actually much more paths, much more valid paths in the grid. At the same time, it becomes a bit more difficult optimization problem. That is something I have experienced.
Volumes bias trade-off again. Because the model is getting to be like more parameters, more complex maybe in that sense?
Yeah, you can. Yeah, I guess you can say that on some level.
So which lever you pick to repeat that is dependent on this particular example? So like say why do you choose like 2 L's? Like which letter do you pick? Like, why not like repeat the E, for example?
The low has one E. But if
Okay, I got
So,
it.
actually, question: if you were doing this in reality, would you be basing it on phonemes rather than letters?
Oh, recently they have been going more towards characters. That's where deep learning has shifted us towards more character level.
Okay, so then you must have to kind of, for some languages like that are non-phonetic and stuff, like that must cost probably.
Yeah, that's true. That's actually sometimes dealt with the language model. You use a language model to deal with that.
So you have a prior over like.
Yeah,
words.
it's basically some sort of prior. That's got it.
You mentioned the valid path. Do you consider that the one that, for example, ends with T, that there's a path of operation to T and T back 8 steps? Because that's a valid path of course.
No, if it contains anything other than the ground truth, it's not valid path. We have to apply our function that we have defined in the beginning. If we apply our function on that path, it should give us hello. That's the only valid path we have for this target.
But in the model, there's a path from the edge at T1, and I can, for example, stop going up and down, and then ending up with the T at T8. I guess you are not doing the training for that one, but that's a valid path.
Yeah. Oh, yeah. Okay. Yeah. So I'm not. Yes, I'm not training that. I'm not trying to maximize the probability of that path. I'm actually trying to minimize that probability.
But do you take care of the minimization of that probability?
Yes. It depends on the model that you have. Here I'm talking about CTC by itself. When you want to apply it in for example, in a normal neural network with a log softmax, usually you would just take the probability output and flip it. That's how it's simplified on paper.
And so the valid path that you have here come from like a bunch of training audio points, right?
No, the valid paths come will depend on the number of time steps and your target, right? So here, because we have because the target is HELLO and we have 8 time steps, these are the valid paths.
Right, but the reason that you can't have a path that ends at T is that in hello nobody says T in hello, right?
Well, okay, yes, that's true, but at the same time, in your labels, you don't have that. You have to provide the labels, right? And if T is not in the labels,
okay, T is a bad example. Let's say the word none of the path end at L, right?
well, the network's output will have all of these characters, right? Here we're taking the network's output, and so the network output will have a distribution, for example, over all letters from A to Z, right, and blank. And so we only take the probability of L, even though it will output a probability for T, it will output a probability for Z. Here we will only take for example, in this particular case, we will take the probability of L at the 5th time step. The probability output, the probability of L output by the network at the 5th time step. I hope I'm clear. Yeah.
Yeah, I want to clarify. What's your training set? Is that you just say a
Okay,
word?
so it's sound. It's basically like sound snippets with the characters in there. But so you have a bunch of people, for example, saying different words. Okay, and that's basically your. So you have the waveform and you have the character inscription. Okay, and basically you just that's your training data. Then you try to learn an alignment over these pronounced words, for example, or phrases or something.
So this becomes like a long sentence and you will get a label for that.
Yeah. Ideally, you want to ease up that part a little bit, so you don't want to have a very large number of time steps in your input. Yeah.
So good as you mentioned. Now typically I have all of those characters at the vertical line and also the blank. And then I start training with the whatever word that I have in my language. Then how that's going to be different the n-gram or 2-gram or 3-gram that we have in any of the problems.
Okay, so
those will be the same things.
Not quite, because you have multiple time steps and you don't know how to align the tokens with the time steps, right? So you don't know where L is going to happen. You don't know how long it is going to be, how many time steps it's going to take, right? You can, so basically the way CTC looks at it is that it's agnostic to the sequential information. It will give you the valid paths, but then as you will see, it will backprop through each and every time step independently. Usually with a language model, you have the word before and the number of time steps equal to the number of outputs. So you have the token and you have its label. In this particular case, you have a waveform, you have multiple inputs, and you may either have a single output or you may have multiple outputs. You don't know, and so that's why you let CDC take care of that problem.
Question. So when you're like calculating the gradients of this, are you treating all the different like decanonicalizations?
We'll get to that point later.
Is it equally probable? Because like there's definitely a prior, like people might actually. Yeah.
We'll see. We'll see. This. Okay. Any more questions? Okay. And so with the backward calculation, it's pretty much the same as the forward calculation, but sort of the other way around. If we want to calculate beta at time step 6 of the 9th token, basically we're trying to calculate the probability of transitioning from here to the end. And this just gives us the beta. Just like the alpha, it's just the sum of the probabilities of the paths. Since we have 3 paths, these are the paths we sum them. Okay. And so let's look at an example where we have computed the alpha and the beta together. Let's say we would like to take time step 3 and token H. We can see that there are 3 paths that get us there. Blank blank H, blank HH, and HHH. So if we convert that to the network output probabilities, we have this sum. And so if we look at the beta, actually there is only one valid path from the 3rd time step to the and so in the final result, we would multiply the alpha with the beta together, and this means that we'll multiply this term with each of those terms individually. Trust me, you get this. And so you end up getting, one thing to note is that you end up getting 2 Y3 sub H, which is actually the node of interest. Okay, you actually get 2 of them. And so if we take it out, okay, we can see that we, for example, in the first row we have blank blank H. If we remove this, it will be E L blank L O. Okay, and so if we apply our reduction function, this is hello. Okay, same thing here. This is hello, and this is hello with someone saying a lot of H's. And so then multiply by the probability of the network's output of H times step 3. And so you can see that all of the paths, if we multiply the alpha and beta together, we actually get some valid combinations of hello. And so we can say that the total probability of all paths going through H at time step 3 is just the product of the alpha and beta at that time step divided by Y sub H of 3. Is that clear how we got it?
Why isn't it divided by 3? Why isn't it alpha times beta divided by 3 times 1?
Okay, because we want to calculate the total probability of the valid paths. And so if we want to calculate the total probability of valid paths, I have to add up each and every path individually. And since I have this this extra term, I just divide.
So you don't do the reduction on those?
Well, I can, but I'm just trying to illustrate the point here.
So yeah. What is the role of like the point of interest? Because like for this instance,
okay, so this this is just sort of an example that would help us figure out what each and every node looks like. Okay, it will just help us in generalizing to the general CDC equation for the backdrop part. It's an intermediate step. Okay. And so let's say that we would like to calculate the loss at a particular time step. Now this is where it's real. So at time step 3, we would sum all the tokens from we would sum up all the tokens from the second one to the last one. In practice, we do it overall, but it's just that these are all zeros. And so in this particular case, we sum from s equal 2 to s equals 6, and we have basically the same equation as we used to have. This is just the more general form. And so in general, the probability of the ground truth label is just this from s equal 1 to the cardinality. So this is basically the reason I had the example for the particular node is just to motivate this equation and to make it a bit more intuitive to understand where this came from.
And there's another summation in the time dimension as well. This is in the state dimension, like
this is in the time dimension. So this would be the probability at time step 3
over the states, yeah.
Yes.
And then you sum up over times as well.
Actually, I don't need to do that because I only care about the loss at every time step. I want to backdrop through every time step individually.
Oh, okay.
Okay.
So wait, I don't get that. So that's probability of hello you're saying.
Yes. So we agreed that this node would give you some paths that give you hello. This will give you paths that give you hello. So all of these would give you all the possible paths for hello.
Yeah.
Okay. And so to get the entire probability of hello, we just have to sum over all of these nodes at a particular time step.
Sure. Then what do you do with that probability?
I then use it to backdrop. We'll see. Okay. So as I said, we would like to minimize minus log probability of hello. The first part is easy. We just the derivative of log of p of hello is just 1 over p of hello. The other part is sort of the more trickier part. We're using the chain rule, and so we have established that since hello is going to be equal to this, we will just take this component. So it's going to be like 1 over yt of whatever token we're interested in, and we'll just take its derivative with respect to k. So sequence of s will be converted to k. Okay, so this is basically the tokens that we have in our ground truth, and here this is just one of the ground truth characters. So it's just 1 over x. The derivative of 1 over x is minus 1 over x squared. This is how the whole thing looks. And we sum, of course, over the characters of interest. I'll give an example to illustrate this point better. But is this approach motivated enough, or are there any questions?
So alpha t times beta t, like that sum does not depend on ykt at all. So that's the reason we can actually that is a constant term in the derivative. Okay.
Yeah. So the whole reason for the alpha and beta calculation is to help us do this step in sort of a seamless manner. Okay, and of course, in practice, all of this is calculated in log space to avoid underflow. So let's look at an example. So here again, we have time step 3 and token h. We have this equation. And so for time step 3, and if the token that we want to calculate the derivative with respect to is h. Then it's just minus 1 over y3 sub h squared, alpha 3 of 2, beta sub 3 of 2. Basically, we take the corresponding alpha and beta of this node and then divide it by the network's output probability of this particular node and square that. Okay? Well, this only happens because h occurs at the only occurs once at the third time step. So let's look at another case where this may not be true, which is at t equal 5. And so here we want to take the network's output of L at time step 5, but we need to take care of it twice. And so that means I will have to take into account the alpha and the beta of this node and the alpha and beta of this node. Basically, that's what the notation means. Okay. Well, before that, any questions?
So yeah, if you were to use this up here, can you just elaborate a bit more on the vertical line or the axis? It seems like the way that you sort them out from the top down, it's like dash the first letter of the main word, like H, and you follow the system. So if you shuffle, if you change the rule, like how is it gonna impact on the whole packets?
Okay, so one of the reasons why this is simple and tractable is that the paths from the time step to the next, they're only allowed to be across and down. If you shuffle them up, then all of a sudden
The rules change.
Yes, the rule changes. So that makes things much more complicated. Okay, any more questions? I mean, we're practically done, so.
And then the result of invariant under the rotation, the front of it.
It's invariant.
Invariant under shuffling, or the order of the letters.
Why would you want to shuffle?
Yeah, it should not be, like, part of the thing is, we just only want to, like, allow for, like, different pauses, but not for, like, completely ordering of phonemes.
Yeah, so it has to be in this order. Like, this is one of the constraints on calculating this. You have to have the order, like, you have to know that H happened first, E happened second, L happened third, L happened fourth, O happened.
I'm just thinking about some words like in the Spanish Poland, right? H and A sounds like similar, like, right? And then, but basically you say that you already know what is a word. What is a,
This is ground truth.
Yeah, you know what the word is.
Yes.
So you
Yes.
don't know which one.
Yeah. You just don't know how many time steps it took the speaker to say, O or La. Okay, so and even for some speakers it would take a few milliseconds, others it would take a bit more. Okay. I'm going back.
Okay, wait here.
Okay.
So what is 6 and what is 8?
So 1, 2, 3, 4, 5, 6, 7. I did not explicitly mention that, but that's the
No, that makes sense.
that's how it is. So to conclude, as you saw, CTC loss allows us to train models on sequences whose number of inputs is different than the number of labels. So usually the number of inputs is much larger than the number of labels. It also makes use of dynamic programming to calculate the probabilities of different paths efficiently. And one sort of disadvantage that's mentioned is that CTC treats every time step as if it was independent. That's why, for example, models are encouraged to be recurrent in order to implicitly capture this information. Okay.